So, but continue. Okay. So we live in this world that has some inherent oppression and discrimination, and then we use machine learning to formalize process in the world, which also like scales and makes it bigger. So it's kind of natural that we risk the perpetuation or amplification of injustices from the system. So, but there is also some hope if we take things into account, if we think carefully about like the implications of our work, we can still have the opportunity to rethink decision-making process for a fairer future. So, okay, some examples. This was from 2018. This is an example where Amazon made a system to score CVs, resumes of candidates applying for jobs. And it turns out that women with applying for technical roles had less scores, were receiving lower scores than men applying for the same technical job. So this system at the end was not implemented like they realized. They didn't implement it in real world, but it was one of the very first news that came out in the topic of unfairness and injustice. So another example is the gender shades paper by Gebru in 2018, in which they uncovered that gender classifiers were have different error rates according to the different skin tones. You can see here for the darker skin tones, these were 3 commercial classifiers, gender classifiers from Microsoft, IBM, and Face++. So these were classifiers that were being used currently and deployed. And for darker skin tones, the classifier was basically performing almost random chance. So this is also one of the first works. And yeah, we might think, okay, it's not that maybe that bad if you are misclassified in gender, but then there are other things that can put people at risk, like face recognition failing, and it happens several times that a black man has been arrested because someone trust a face recognition system that decided that that person was committed a crime, right? When the person was innocent. So because of errors in face recognition systems that tend to underperform for certain demographics, people can be sent to jail. And this is another of the big controversies on bias and fairness. It's called the Compass system, and this is a system used in the US for criminal justice, in which a model gives a score to people that has committed a crime, whether they are likely to commit a crime again or not. And ProPublica made a report and find out that it was giving higher chances of committing a crime again to people, black people, higher than white people. So, okay, given those examples, I'm going to introduce now 5 different types of harms that we can perpetuate with machine learning. The first one is allocation, which is, it means that systems that extends or withholds opportunities, resources, or information for certain demographic groups. So that could be the example of Compass, for example, like if you are unfair to certain demographic group, black people, let's say, and assign a higher criminality score, this really affects their lives and their resources, or even like the possibility to be sent to jail. Another type of harm is quality of service, which is whether the system does not work equally well for different groups. It has different implications. Maybe it's not so harmful, but still, like it can feel very unfair for people that the system provides lower quality than to other people just because of some group that they belong to. So another type of harm is underrepresentation, in which certain groups tend to be overrepresented. An example of this is, for example, for image generation. If you input a photograph of a CEO, most image generations will produce representations of white men. So it's again like overrepresenting a certain group with respect to even like the real distribution of the world. The next type of harm is stereotyping, which are systems that reinforces stereotypes. Also, like image generation can be an example of this, or even like machine translation. When you try to, it has happened in many occasions when you translate from a language that is gender neutral to a language like English, which has pronouns. Many times if you try to translate he or she is a doctor, then it's translated to he is a doctor, reinforcing stereotypes of gender or any other oppression. And the last type of harm is denigration, where the system is actively derogatory or offensive. Like, for example, object recognition, Facebook systems, in which a few years ago they were misclassifying images of black man as a gorilla, I think, or something really, really derogatory. So the point is, like, these harms are not mutually exclusive, so different systems can have different harms, even for different groups can perform different harms. Another point to make here is about intersectionality. So discrimination might occur at the intersection of different groups and not just within single groups separately. And for this, I'm gonna show an example. So this is a case from justice in the US, in which a black woman sued General Motors for discrimination because they were not hiring her. And she said that they were not hiring her because she was a black woman. And then General Motors showed in the trial that they were employing black men in industrial and maintenance roles, and they were employing white women in secretarial positions. So at the end, the judge dismissed the case, said that General Motors were not discriminating anyone because they were hiring both black people and they were hiring women, so they were not discriminating based on race and gender. But the point here to be made is that they were not hiring any black woman, right? So the intersection also is something that it's important. We need to look at because single groups might not be the whole story. And this is something that the Gender Shades paper did. They looked also at the intersection of how, like, the gender classifiers were working for skin tone and gender. And then they found out that for darker female, the misclassification rate was up to 35% difference than lighter male. And this is something that you can only find if you do, like, the intersectional analysis and with the subgroups interconnected, because otherwise female and male will not don't have as much difference. So it's when you really look into the intersection when you also find these big discrepancies. Okay, so why unfairness in machine learning happens? This is a very important question, and usually the simple answer is, like, because data sets are biased or data sets are not perfect, but the answer is way more nuanced than that and have many more layers. But the answer is not bad intention. So no one is creating models thinking like, I'm gonna discriminate against women or against black people. This is not happening. Like, bad intentions is never the answer or why machine learning is unfair. So the thing is that we live in a world that has some historical discrimination, and then we get data from this world. And when we get data, the fact of getting data, the fact of categorizing people, classifying instances, it's already it's already introducing some biases on our perception of the world. Like, we cannot, when we build data to train a machine learning system, we always do simplifications on our data. It's impossible to capture all the nuances of the world. So by doing these simplifications, we are already introducing selection bias, annotation bias. And then we train our machine learning model, which also can introduce algorithmic bias. So it's not only reproducing the bias in the data. So how we train our models, which metrics we optimize for, like the rewards that we put in our systems, are also introducing algorithmic bias. And then the cycle is closed by the decisions taken by the models being affecting people or, like, the real world. So this comes back. It's the cycle. Okay, so to recap this part, fairness in machine learning is a fundamentally socio-technical challenge. So we cannot approach this problem purely from a social or purely from a technical perspective. We need to broaden our scope. Many times it's not just like I do a change in my model or I clean my data and then the problem is solved. We need to really understand the context and why discrimination is happening. This is because there are many reasons why unfairness in machine learning happens. And to solve this problem, it cannot be treated as an afterthought. So it needs to be prioritized, and put into action at the very stage of the life cycle of the models. Yes?
Wait, it will come. I mean, so far we are discussing only like the problems. And yeah, but the problem is like not defined for me. That's what I'm trying to say. Wait, it's informal.
No, it's a very valid question. Yeah. I'm not. Yeah. No, I think it's a valid question to have now, because I don't have like a definition of fairness. So, and it depending on the context. So this is all context based. So it's about like considering the harms that your system can do to people.
Now look, we can kind of just explain it in some simple terms. So machine learning is statistical, right? So then you have some examples that somebody sued for the decision made for them. Machine learning cannot have individual guarantees. There will be always errors, right? But it might have guarantees for some subgroups of the data. And this is what you're talking about. So some group of people who have black skin. And then what is happening for the people with maybe with the black skin, maybe there is a statistics in the real data such that they are less likely to be productive in their job, and then the company, to maximize the return in the short term, will kind of be hiring them more. And there is nothing wrong with the machine learning from this side. But it's now why it is social ethical, right? So it's that maybe then because you want to impose some policies of our society building into the machine learning that will say, okay, you are not allowed to take a shortcut to judge about like the criminal potential or about the job skills just based on the color, right? So you want it to think deeper, not to take the shortcut, and in some sense to be fair if you consider different like subsets of all of your data. So
let me take the question, follow up and the question. So, okay, so fairness seems it's related to discrimination. Okay, so statistical model has different error rates for different groups of your data. This is translated to discrimination against some category. So is fairness always about discrimination, or again that's like only one view of it?
No, this is one view of it. So if we go back to the 5 types of harms, this has to do with allocation and quality of service, and maybe over and under representation. But for example, for denigration,
That's not discrimination.
it's more about like association maybe of harm words, or like you can think of like a chatbot on Twitter, like just being very nasty and offensive to people.
So this
Yeah.
slide is kind of like the answer to Jan's question. Like, it's not easy to come up with a concrete, short definition of
Mm-hmm.
Yeah, which is not machine learning problem per se, it's more social problem.
Correct.
And now we are just trying to, these fields are trying to meet and do something about it. Let's say, let's put it like this. This is my understanding of what you said.
Yeah.
Yes, because from these examples, it seems that it kind of learns the biases and unfairness that exist in the society and translates it in the future. And that's undesirable. Yeah. And the other thing is that maybe the model is taking shortcuts, right? Instead of thinking of the skills of the person, how good he's qualified for the job, it's looking at the statistics, okay, clerk, don't go away. Yeah, something like that.
Yeah, that's a very good point. Like, I'm not sure if I have included this in my slides, but in general, any shortcut that the model can take, they will take it. And in general, that means that even if you try to not include any information about, for example, gender in your model, they will find shortcuts to take that information into account, because like our data is biased. Like you might, for example, like you might not include gender into a system that tries to predict a score for hiring people, but still gender might be correlated with how many years they have spent coding, for example. So the system will find the correlations, if there are. Okay, any other question in this part? Okay, so then let's move on then how to assess fairness. This is, I will introduce, okay, I'll say again later in the slide, on the corresponding slide, but we will talk here about three criteria to measure fairness. So let me first introduce the notation. X are the input features, Y is the outcome, R is the score function, and then we make a decision based on a threshold rule. So for example, let's think that we are trying to predict a hiring outcome giving a candidate resume. So the input features can be like the years of experience, qualifications, and so on. The outcome is going to be whether the employee is a good employee or a bad employee. This is already a problem, because how we know someone is a good employee or a bad employee if we don't hire them? The score function can be any supervised classifier, and then the decision is whether we hire them or not. So as preliminaries, we have the decision metrics, where we put the decision made by the classifier and then the outcome. So we have true positive rate if the decision is positive. So if, for example, if we hire someone, given that it's a good employee, false positive rate if we hire someone but they are a bad employee, true negative rate, and the false negative rate. And with this, we can start playing around with the fairness criteria. So we will see, we also need a random variable that encodes the membership in the protected class. So for assessing the fairness criteria, we need to know the different groups. So we need to know if, for example, we are assessing fairness in gender, so we will need to have a variable that accounts for male, female, non-binary, whatever the classes that we decide. So A can be correlated with X, because, or even part of X, so that's not a problem in our criteria. And then the aim is to equalize different statistical quantities involving this membership A. So there are three fairness criteria we're going to talk about. There are the main fairness criteria in supervised classification tasks, equalizing acceptance rate, error rates, and calibration. So the first one, equalizing acceptance rate, it's also called demographic parity. And it says that for two groups, A and B, let's say male and female, their acceptance rate needs to be equal. So this is the formula. And the generalization is that the decision is independent from A. So let's imagine this is the hiring scenario. This means that whether an applicant is hired should not depend on gender. So a priori seems like a very natural thing to ask. Good, seems good, but let's check a bit more. This does not outrule fairness. Why? Because you can still make good decisions in one group, but poor decisions in another, and still have equalized positive. So, for example, if we are trying to predict coronary risk disease, this score was created for white men. So it works super well for white men, and then it's applied to other demographics, and it's working way worse. But at the end, you have the same rate of people that is classified as having the disease. So there is an intuition here that we can see that we should not match true positives in one group with false negatives in another group. So we should, it's not only about like how many people passes the threshold, but we should have some notion about the errors as well. So the second fairness criteria is equalizing the error rates. This metric is also called equalized odds, and it says that for any group, their error rates needs to be equal. So we equalize the false positive rate and the false negative rate. So here the generalization is that D and R are independent from A given the outcome Y. So we can think as an example that a classifier should neither falsely reject suitable men compared to women or unsuitable candidates of any gender. So it's about the error rates. The problem with this is that it's a post hoc criterion. So it's nothing that the decision maker cannot know who's a positive or a negative. If we are thinking about the hiring example, you don't know when you are making the decision who's gonna be a good employee or a bad employee. So this error rate is something that you can only apply at hindsight. So after, I don't know, the first evaluation of the employees happen, then you can assess whether, like, for different genders, the error rates match or not. But when this happens, the decision has already taken. So then any difference in the error rates can feel super unfair for the people that are in those groups. So because it feels, the intuition is that it feels it would be better that the misclassifications are equal in all the groups. So that's also kind of the problem with this metric. So the last metric is calibration. And here, the thing is that we calibrate the score. So the small r belongs a probability. So we pretend that r is a probability. So the score value r corresponds to the positive outcome rate r. Like, r doesn't have to be a probability, but we just pretend it is. And then we can calibrate by group, which follows from y, which is the outcome, independent from a, which is the group, conditional on the decision, the score function. So what this means is that we don't care about the group anymore in calibration, because it means that the score that we get means the same for any group. So then we don't need to make any mental gymnastics. If I get a score 0.7, I don't care anymore if the groups are calibrated, which group it belongs to. It's just a 0.7, it's the same for everyone. Yeah, but that's a consequence. Like, then if it's equal, if it's calibrated by group, so if you look into each group and each group is calibrated, it accomplishes this fairness criteria. Is it related or the question? Ah, okay. Sorry, second.
Just like, I'm wondering, like in your example here, how do you calibrate it? Because if you want to calibrate like probability that he's a good employee,
Mm-hmm.
that you would need to hire that person for some time, evaluate it, and so on, and you would need to hire people which you wouldn't hire otherwise. So
Yeah, yeah. Yeah. Okay. Yes.
So just to understand better, so the classical calibration is a property of the probability distribution. If it is the ground truth probability distribution, we are good, it's calibrated. It gives us the right probability statistics. And then we could use it for decision making in some fair or unfair way. So this is kind of decoupled from fairness. But what you say in this calibration by group, it says it's okay, so we are now going to enforce some other property that says that our predictive probabilities should be independent of the group.
Yes.
And this is like how it is enforces.
Yes. Exactly.
Okay.
Yeah. Yeah, because then you can forget about the group. Then your R, it means the same for any group if the groups are calibrated. So a 0.8 score means the same if you are a black person that if you are a white person, if the groups are calibrated. Okay, so it's a priority guarantee. So this is the example, like if we have a 0.8 score, it means that 80% of heart disease on average, over people who receive, there is a 80% of risk of heart disease over people who receive a score of 8.0, so it doesn't depend on the group they belong to. But this is at the group level, so it's not individual level. It doesn't mean like if I get 0.8, I have 80% chances. It's at the group level. So to recap, there are these three metrics, equal acceptance rate, equal error rates, and calibration by group, which by looking into them and like high level, they all look like they accomplish some notion of fairness. So the question is like, can we have them all? Like that would be ideal. We have a system that then we makes accomplish all these metrics, so we're good, we are very fair. But there is an informal theorem that I'm not gonna go into the mathematical details, but basically we cannot have two of these criteria at the same time. So they are mutually exclusive. And that's why fairness is such a complicated topic to discuss and like to compute, because it really depends on the context and what criteria you want to achieve. And for this, I have an example. Coming back to the compass debate and the compass example, I'm going to explain again. This was a system that was assessing people that has been set as criminals, how probable they were, or yeah, they were scoring people on how probable they are to commit a crime again. And then there was this ProPublica report in 2016 saying that this system was biased against black people. So what ProPublica did was to look, after some years, to look into the people that have high risks, whether they committed a crime or not. And then they separated into two groups, black people and white people. And then they found that black people had higher risks while not committing as much crimes as the white people with the same risks. So this is the criteria of not equalizing the error rates. So they concluded that black defendants are more likely to be labeled as high risk. What happened next is that Compass said that they have calibrated by group. And it's just that black defendants have higher recidivism rates. And that is something that they cannot do anything about this. So this is an example of like two fairness criteria being contraposed. Like you cannot achieve everything. Then the question here is like maybe why black defendants have higher rates of committing a crime again. And there is this whole debate that maybe the data that we're using was already like very, very bad data, because in the US, the police tends to arrest black people with higher rates than white people, so then the rates are already biased from the beginning. So a word of caution, there are non-fairness metric rule, so fairness metrics and fairness criteria doesn't rule out unfair practices. This is just some guidelines. And they are not meant to be like fairness certificates. It's like, okay, we have equal error rates in different groups, so okay, we're fair, we don't need to care anymore about this. This is not how it works. And also, very importantly, we should not optimize fairness criteria. They are not good objective functions. If we, for example, try to optimize for equal error rate, what probably will happen is that for the group that has lower error rate, it will just like produce more errors. So that's also like the result will be kind of unfair for the group that was already doing good. Okay. Next is the mitigation approaches, but if you want to discuss anything, no? Okay. Okay, so the last part is about mitigation approaches. So given this, what we can do, I'm gonna talk about three aspects: data, algorithms, and applications. So data. Many issues in fairness are rooted in decisions surrounding the data, how we collect the data, how we categorize the data, how we annotate the data, how we clean the data. There are many decisions that we make with our data, what our data is based on. Many of our decisions are based on previous assumptions from previous data sets. For example, like ImageNet is based on WordNet, for example, which problems might also be with WordNet. So some mitigation techniques, this is not comprehensive at all, it's just like some ideas, maybe we can discuss more, would be like dataset documentation, dataset audits, and dataset balancing. But the key question that we should be asking ourselves is who is represented in the datasets and who is left out. I think this is the most important thing, especially when we are dealing with data that involves people. And most data involves people. Even if you don't have people in your dataset, most data involve people because affect people. Even if you have an object recognition, this will affect people in somehow. So for documentation and checklist, Gebru's paper on datasheet for datasets, it's fundamental. So these are datasheets or checklists with a lot of questions about how you collected your data, who is represented in the data, how affects people, how are you gonna share your data, and a lot of questions that makes the dataset owners to reflect on the data practices, and then future users can understand the use cases and see the potential risk when applied to future applications. So this is not like a mitigation, but it's about awareness and transparency. Okay, and dataset audits are super important. Abeba Virjane has done a lot of work on these regards, because if we don't know what's in our dataset, then everything can go wrong. So this is a paper from 2021 in which they audit the Lion dataset, and they found that it has a lot of problem with the data. But not only like there was a lot of non-safe for work content, like it's blurred here, but the associations, like you can see like here, the word that they searched for was mommy, and the content that they found was related to that word with highest scores, or the highest scores was non-safe for work and pornography. So if no one is looking into what's inside these big data sets, we are just training our models with this. So data set audits are a fundamental part in this thing of fairness in machine learning. So the next mitigation approach is related to algorithms. So some mitigation techniques include regularization, optimization, so adding constraints to our training losses. There are many work on representation learning, like trying to, from your input data, trying to project to a space that is independent from your groups and your attributes. Still, we have seen that this might not always be the response. Independence is not always the response. There are techniques for training on synthetic data. So if you know that your data is problematic, you can change. If there are some correlations between, I don't know, gender and objects, you can synthetically generate different gender distributions and try to train your algorithm. But yeah, so the key question here is that algorithm approaches might still introduce unwanted biases, and I have an example. So this is for image classification example. This was one of the first papers in 2008 talking about biases in image captioning. So what they show here, so image captioning, we input an image to model and we generate a caption, a description of the image. So in the first image, I don't know if it's maybe too small, but the caption, the baseline model generated a caption, a man sitting at a desk with a laptop computer, and the person that we see in the image, it looks like a woman. I mean, perceived woman. So the caption was misgender, right? Like it's saying a man when there is a woman in the image. So the authors of the paper look at the model attention maps, what was happening when the model was misgendering the person. So when the model was predicting the word man, the model was looking at the computer. That was what was happening. So the model didn't look at the person to predict the gender. It's just like the model decided there is a computer, so the person should be a man. So what the authors proposed was an equalizer, the bias method, to ensure that when the model was producing a gender word, it has to look into the person. So then they modify the image. The image on the top is the normal image, and the second image is the image removing the person. So in theory, in the second image, you should not be able to predict the gender. So then they imposed these constraints in the laws, and the result is there, right? Like they could reduce gender misprediction while also like ensuring that the model was attending to the correct part of the image, so the person. What happened, that's what I wanted to bring up this example, is that a few years later, we have a paper in which we show that the model was really, this kind of model was really having a lot of shortcuts. So from this image, for example, the baseline is a man standing next to a fire truck. And then when we apply this regularization, yes, the model corrects the gender. But what happens next is that the rest of the caption is full of stereotypes. It's not even corresponding to the image. So it's not as easy as like, okay, I add a loss here to solve this problem, but then other problems might arise. So this is what happens with fairness. Okay, and I'm finishing almost. So the last part is about applications. So sometimes, not always, but sometimes the issue is not how we predict, but what we predict or that we predict at all. Maybe some applications are better approached without machine learning. And I'm saying this as a machine learning person. But still, maybe machine learning is not always the solution. Maybe some applications should not exist. So this is also some thoughts and some debates that we should have also as a community. However, it's not straightforward to distinguish what technology should or should not exist. But just as an example and an exercise, let's say this is also a problem with the US. Sorry, all the examples are very US-centric. Failure to appear in court. So apparently there is this problem that there is a trial, and then they decide someone to come to court, and some people don't go, so this is a waste of resources, time, and so on. So one approach could be, okay, so I have my historical data, and I try to predict how, give a score, whether a person will appear in court or not, and if the score is high, I'll just put them in jail or retention or whatever to make sure that the day that they come, that it's the trial, they are there. Okay, but maybe an alternative is to recognize the problem and why people fail to appear in court. Maybe it's because they don't have childcare and they cannot leave their child alone at home. Maybe there is not enough good transportation. Maybe maybe because they got deported. Maybe because they cannot leave their job because otherwise their boss will fire them and then they cannot pay the rent. So if we recognize this, maybe we can be able to implement steps to mitigate these issues. So this is not a machine learning solution. But yeah, so so what can I say? Like, clearly some problems might be better addressed as a society without predictions and without involving machine learning. I'm not saying like we should not use machine learning. I'm a computer scientist myself. But maybe we should rethink what we do with data and if everything needs to be datafied. So wrapping up, this is the last slide. Yeah, many settings like criminal justice or things that really affect people's life cannot be reduced to a mathematical criterion. Like our mathematical criterion as statistics don't account for context, don't account for historical discriminations. Unfairness in machine learning is not just a technical problem. So this is what we were saying, like it's at the intersection with social science, even legal systems. But I truly believe technical people need to be involved in detecting, assessing, and mitigating the discrimination harms of technology. So that's why it's so important to have these discussions in these kind of courses on deep learning. So if you are interested in the topic, here are some very good resources that explain the thing way more better than me. And that's it. Yeah, it's super clear and very good question. No, like there are many uses of legitimate machine learning that will help people, but they are still have fairness, and it's a very big problem. For example, to put a concrete example, let's say we are trying to detect skin cancer from images. Like that's something like if we can do that with machine learning, that would be amazing. Like it will help people, but still like people with darker skin tones, their detection rates are lower. So their error rates are higher than lighter. So if we are building something like this, we really need to make sure that works for everyone.
One question, just the message is like fairness is fundamental. It should be a basic, fundamental principle of machine learning. And then at some point you said, okay, like this fairness metric should not be treated as an objective. We should not be optimizing this objective. Yeah, you need to go back to the basics. But if you're ending up with a given data set, yeah, and that's your training data, the best you can do is actually optimize the metric, right? Or am I getting the message wrong? That you need to go for balanced error rates, which means you need to assume that during test time you have a uniform distribution. Right, because if you cannot go back, to redefine the task, the data collection process, optimizing this metric is the best thing you can do.
Normal. I mean, it's a very case by case field actually, but normally the answer is no, because normally it will take shortcuts and it will never do it in the proper way that you want the model to do. That's the problem with data-driven systems.
To me, the current best way in practice is to collect more data or train a more accurate model. And I don't know if
I think that's the message, today, but I was wondering if you're dealing with the case that that's not really enough.
Maybe solve all of these problems. Like if the bank is deciding whether to give loan or not, they are maximizing their return. So for them, a best performing model, you will not necessarily need to hire these subgroups of people.
Still have some time to go. Thank you.
Thank you.
Am I there? No. Maybe this is. Yeah. Good, good, and this. Okay, so not an exhaustive list, but normally, you know, these are some of the basic aspects we focus on when we talk about responsible AI. So the first one, maybe I should here modify my slides. That it's like, you know, fairness is just about discrimination, yeah. So fairness was covered, and then other aspect that we will go through and talk is explainability, the ability to explain decisions and mechanisms of the model to humans, privacy, security, environmental impact, and the end accountability. Okay, we're not covering that. That has to do with, you know, a very important topic with regulations. Okay, who is accountable for errors of a machine learning model? So we're not covering that today. It's basic, like, you know, something that belongs to another principle mostly, yeah, if not fully. Explainability, actually very related. It's good, you know, as a follow-up to what Noah talked about, because the message here is like we cannot always blindly trust the predictions of the model. Yeah. Here, hope some really, you know, easy to understand, convincing examples is that you have a case of a deep model trying to predict COVID from some X-rays, and the model did shortcut learning. It was easier to decrease the loss by focusing not on the useful signal on the X-ray, but on the watermark that some hospitals had on the whole X-ray that was scanned, and this was not cropped out. Okay. So indeed, you ended up with some, you know, reasonably good accuracy, but if you cannot understand the mechanism of the model, then, you know, you don't see that it does nothing meaningful. Yeah. Other cases where here is what, like, you know, a model to detect whales from audio files that actually logs on other signal, yeah, that maybe a human cannot understand, but it's on artifacts, on some noise. What happens there is that the model is actually capturing correlations and not causation of, you know, what is actually the information in the X-ray that indicates that this patient has COVID. So there is, you know, secondary importance, you know, put on this rather than the easy shortcut, which is the watermark. So the message here is that, you know, you need to have a mechanism to understand whether the model is getting some shortcuts like that, or what is the way to provide the predictions. There's for sure many sensitive domains. Justice was mentioned, yeah, healthcare and so on, domains that maybe it's not a good idea, yeah, anyways to implement and integrate machine learning models. But if you do, explainability is important. Well, models like ChatGPT, you know, fall also in this category. We often make questions, we get answers, and have to accept them. Have to accept these answers as given, as if, you know, ChatGPT is a god that knows, you know, everything, doesn't need to justify the answers, the sources, and provide, you know, a tree of information that led to this answer. So that's actually, you know, quite dangerous. So again, here another aspect where it's not easy to strictly, you know, concretely get a definition that everyone will agree on what we're after. Even there is two different terms in the literature: explainability, interpretability. Some people try to use them differently. I would say the conclusion is that they can be used interchangeably, yeah? And today we're referring to the same thing by those terms. And maybe, no, a simple definition for today is the ability to understand how the model makes decisions, and why the model produced a specific output, the output to a specific input data point. And this is essential as a debugging tool. If your model is doing shortcut learning, then such tools give you a way to understand that and then go back and fix the model. Yeah, we're talking about not code debugging, but debugging of the inference and the reasoning process of the model. It's useful for social acceptance. Yeah, if humans can understand somehow, get ideas, intuition about how a model works, then it's easier to accept it. It's easier to integrate it in parts of everyday life. And at the end of the day, it's essential for human and machine interaction, because Noah mentioned it's a very bad idea to implement machine learning models in some domains,
for sure not fully automate them, but having like maybe a tool with a human in the loop, and the human actually maybe, there will be some cases of some people having very high probability of not appearing to court, and then there is a judge actually behind this model, and now, okay, a red flag appears because someone has very high chance, but the model needs to be able to explain, okay, I'm producing high probability here for those reasons. Why is progress in this field? Even though it sounds very essential, progress, okay, is a bit slow, or maybe not as much as someone would expect for such an important field, because there are difficulties, yeah? How to progress, how to evaluate what we can do. There's lack of ground truth. We don't know the exact, we're after the exact reasoning process, but we don't know to create ground truth for that. And there is subjectivity involved because it's about explaining the decisions to a human. So these are already, very, important, how to say, obstacles in evaluating the explainability of models. Lack of concrete ground truth, yeah. And anyways, yeah, it's more of a philosophical problem to some extent. Now, very vague, let's say, illustration of what is happening is that the bad news for deep learning is that, the deeper, the more complex the model, performs better, but each interpretability dramatically drops. It's not like the simplest case of a linear model where you might be able to get some understanding about, what are the input features. Maybe these have some intuition because they come from, some measurements in the task, and what is the weight for each of the features that causes the prediction. Okay, so the bad news is that deep learning models are very, very far from such a case. And that's an illustration like from a paper that corresponds to machine learning models in general, that you may have explainability by design of the model, or to add it post hoc, like after you create it and train the model, and can be model agnostic or model specific, explain local predictions for particular data points, or in general the global reasoning of the model. Again, the bad news is that for deep learning, such thing is really not an option, so we're dealing with post hoc solutions, and typically most of the times model specific ways. So, okay, how one approaches this task? Yeah, sure, yeah. Yeah, good. So it's a question. Okay, good. Very, very good point. You ask ChatGPT, how come? Yeah. Yeah. Right. That's indeed like as a feature, it qualifies, right? It is able to explain in a human understandable way. But again, like it's a bit of a chicken egg problem because now it uses the same prediction mechanism, the same prediction mechanism, predict the next most likely word to appear in this sequence, to give you the answers. Good point. So it qualifies as a feature, but now it's a question, okay, can we evaluate that? Is it valid? There's problems in evaluating. So probably something else is missing. So we're... Uh-huh. Yeah. So that's exactly where we're heading, right? And trying maybe to answer like two useful questions also. Normally which parts of the input are responsible for a particular prediction, particular input data point, or which training examples are responsible for this prediction. I'll try to do that with an example that I think has some good take-home messages. So maybe that's how an interpretable computer vision model could look like. That's a test example. and then like it focuses on particular regions and it tells you, okay, like actually this region of your test image looks like this, that comes from a training image that carries this known ground truth label, another one like this class, or another one like the same class, and so on. And at the same time, you might be able to get some extra information about, okay, now the part that I identified from a training image, you know, has some high resemblance to this part of your test. So again, qualitatively, someone, you know, can say that this is, you know, more understandable to a human than just getting the predicted probability and the predicted class. Okay, so it's a way to explain some of the internal mechanisms of a model. Again, I'm saying it's more understandable, right? Again, no concrete way, not clear way to evaluate. You know, what is more understandable? What is more explainable? This is like, you know, a big challenge of the field and a big, like, you know, ongoing problem. So, two typical ways of doing that is that the model itself is not interpretable, but the prediction or part of the prediction process is. A simple example is that nearest neighbor models are easier to, you know, interpret. I'm predicting this class because the nearest examples, given some representation space, the nearest training examples are those ones, and I can visualize them, I can rank them, I can give some, you know, predicted similarity for those. Okay. The problem is that still the representation model is not explainable at all. It's some deep model, some beast model that has tons of parameters. Okay. And then often one needs to replace, you know, like some parts of the model with more interpretable ones. So it's again there, you know, bridging between, you know, what can a human digest and understand as a, you know, reasoning process of a model, and then try to inject such a design. So trying to, you know, motivate those, you know, those cases through a particular example. But actually here it's a deep convolutional neural network. Okay, so up to here everything is very common. We're getting the 3D tensor representation of an input image. So we can see this as a collection of local representation, right? Like we have, this is typically W times H, yeah, width times height times depth. So we have that many local descriptors. Yeah, each one corresponds to a region of the image. And then this, you know, computes the similarity with some regions from the training images. Yeah? And in the end, there is a max pooling process. So this tells you, okay, that there is at least one patch that is that much similar to a training example, okay, to a training prototype. So that's the max pooling process, that it will keep just one of the similarities. And then this comparison process happens for many parts of all the training images, okay? So this is some kind of nearest neighbor process. Say, I'll compute, you know, all the similarities, yeah, and I will see what is the closest patch from all those to the training prototype. And then now this vector of similarities, yeah, similarities to the parts, the object parts from the training images, is passed through a simple fully connected layer. It's a linear classifier, so you will predict the scores. Okay. So this is a design that, you know, brings some internal mechanism closer to what a human can understand. Okay. How similar are parts of this image to, you know, common parts of the training examples? And then let me transform this, you know, in a linear way, so it's the simplest possible model, to the class probabilities. So now, you know, if you start to train this, you know, the question is, how do you train such a process? Okay. So one thing is, if you train this end to end, typically you will have like a representation here that you need to match a vector, this vector, with all the vectors here in this representation. Okay. But this one, you know, lives in a latent space, and you optimize it's a continuous space. It doesn't correspond to a particular image region. So what the authors of this paper are doing is that, you know, the training is split into different stages, and at some point you project, you find actually the nearest prototype that corresponds to a real patch. Yeah. And then you can continue the training. Okay. So there is an iteration between these two steps. Okay, I optimize everything, but then at some point I project, okay, so maybe this is similar to what happens in projected gradient descent, that I have a set of feasible solutions, I project there, and then I continue the training. Plus another process to make it more understandable to humans is that the whole training freezes, and now these weights are modified of the classifier to be more intuitive to a human. What that means? Sparsity, many zeros, and no negative weights, because these negative similarities that like, okay, this is likely a black-footed albatross because it doesn't look so much like some other classes. So this is less intuitive for a human. So therefore, the training process, the training with backpropagation pauses, and then there is some optimization that changes the weights. And then for these frozen weights, you go back and you reoptimize the network. And for instance, like in such a process, the authors in their paper made some relation between the discrepancy that is caused by projecting to the real patches. Yeah? You replace a vector with another one, even though stochastic gradient descent says, okay, it's this vector that I'm using to optimize the loss. You project to another one, so they made a relation between this distance and actually the influence that it has on the predicted probabilities. Therefore, you can have some estimates about, okay, what kind of change can destroy your predictions. Okay, so here a different design process. Nearest neighbors are more interpretable, and let's change some parts of the model so that again they're more interpretable. Another common example in the literature has been explainability maps, right? Yeah, saliency maps. Let's indicate for each part of the input, for each pixel, how much it contributes to predicting a particular class. Very common early example is that, okay, yeah, actually the gradient gives us some information about that. We have the predicted logit here. Let's take the gradient with respect to every pixel. Large magnitude seems that like if I change there, it will affect the loss a lot. This is visualized here. What we observe is that it's actually quite noisy. Like, yeah, it really varies across pixels. So taking predictions at pixel level was not really helpful. Another way is to mask out some patches and feed the image again to the network and see the change of the predicted probability. Yeah. So again, that's another way to estimate the contribution of this patch. If it's important to predict the class wheel here, then when I mask it out, the probability of the class wheel will drop. And that's what we see here. And these are computer vision examples, but you can imagine similar cases for text and natural language. Right? You have a sentence and you make a prediction whether this is a positive or negative review, and you mask out, you remove words, and then you see how the prediction is affected. Maybe here we will just skip, but okay, different kinds of approaches to create such explainability maps. Maybe another useful example is what is called the counterfactual explanation. So putting it high level is, what should I change in this input example, so that the prediction changes from X to Y. So that would be, this is an example from this class. What can I change? What can I borrow from this image that comes from another class so that the prediction of this will switch to red-faced cormorant. So that's the high-level description, and then researchers, the authors here, design an optimization process that reflects that. And actually, maybe what is more interesting to say, what is the minimal change that someone can do? Okay, so that you will find the most important differences. And this was expressed by, let me have a combination of the image features of the original image, with the features from another one. Create a permutation matrix, which means every patch can, be replaced by any other patch of the other image. And there was some optimization, just to say briefly, that This needs to have some sparsity, yeah, alpha, and also be as close as possible to binary, yeah, that you're taking a patch and you're replacing it and you're putting it in the other image, and do this for as few patches as possible. So if it's not clear yet, let's see through examples why this is helpful in understanding, what the model does and if the model operates as expected, which maybe is not the most necessary thing for digits, but it's actually more intuitive. So you see here, you take digit 1, let's say it's recognized as 1, and we say now, what can I swap, what can I borrow from this image so that the prediction of this will become digit 4, okay? And then the authors also did a feature combination, but then they had a way to compose an image just to present this to a human. And you see that actually what it borrows is actually meaningful, and it resembles the way that this task happens for humans as well. Which at the end of the day is more useful for other domains, where you see here such a replacement of the head, which means that this is the most important feature. Once I remove that, the probability starts to drop, and I replace it with the head of the other one. So, to differentiate among those two classes, the head is the most distinctive feature in terms of parts of the original model. So now, just to motivate this a bit through our own work, okay, and why sometimes this can be useful. We haven't done that, but we haven't worked on explainability for this model, but we have a model that estimates the similarity between two images to do retrieval. So that's the query, and then you rank those images. And we had an approach where, okay, this image was ranked before that many negatives, that many wrong ones, so it was really not top ranked, or that many. And then after we developed the process with, Pavel that is sitting here on the second row, only 7 negatives were ranked before it. So the model was really able to tell that the same object appears in those two images. So why is explainability useful here? Because here also ourselves were like, what the hell? Really, was the model able, with such low resolution, such a small object, to make such a difference between another approach? So is this happening for the correct reasons? Is there some shortcut? So such an explainability model could be a tool to understand your method and improve it further, and maybe find artifacts such as shortcut learning that might be happening. Now moving to the field of privacy and security, and maybe I can motivate it with a non-deep example. Actually, it's an example almost 15 years ago from my former colleagues at INRIA in France, that I think it was really ahead of its time. We're working with SIFT descriptors in computer vision, some handcrafted model for descriptors, and there was a belief that, okay, if I give you the descriptors, then this is like a way to protect the privacy, the content of the images. You operate with descriptors, we can exchange descriptors, fine, you don't know what happens in the image themselves. And back then they were showing that from those kind of handcrafted descriptors you could reconstruct the image. And there are some fields where there can be some sensitive information, and we're not supposed to do that. So in the field of deep learning, this is called model inversion attacks, okay? It's called an attack in the sense it's not, the standard desirable thing that someone would want to do. So then it's like, do I have ways to obtain the inverse function and be able to map the output to the input? Okay, despite the fact that this is like a huge model, and there are approaches in the literature that indeed, given a lot of input-output examples, they might try to train the inverse function. But what is more common is optimization-based inversion, which hopefully you're already very familiar because there was a lecture in adversarial attacks. So that's a pretty similar formulation, right? That you're saying here, okay, I have a loss on the output. That's a given output. Someone, let's say, gives me the features, the 3D tensor representation of this image. I have access to the model, and now I have an image that is composed of learnable parameters, so I'm optimizing the pixel values. I have a loss, so I want to be as close as possible in that. And I'm optimizing X. Plus some useful regularization that you typically, it can be task domain dependent. And here what happens is that for a convolutional neural network, if I give you the 3D tensor representation, yes, actually I can invert pretty much, a lot of information about this image. Okay, now if you're thinking, okay, why the hell, in how many cases would someone give you, share this 3D tensor representation, right? So, but that's hopefully a convincing proof of concept, and then we can move to other more sensitive application domains where you have a face recognition system. And you have access to the model, yeah? You don't have access to the training data, but now you know the output space, and now you're saying, okay, let me try to reconstruct what does the face look like for this class, for this person ID. So now the output, you can't design it. It's a one-hot encoding of a class, and you're doing inversion. And now the regularization could be, okay, here in this regularization, someone could have, cost like total variation, which is nearby pixel, should not vary that much. But in the domain of face recognition and faces, one could have other prior knowledge as well, how a face looks like, yeah. The face parts, someone can have a discriminator there that keeps telling you, okay, what you're generating doesn't look like a face yet. It doesn't look like a face yet. So that it will get better. And there is work that shows that, okay, indeed, you can recover sensitive information. You can recover training data given the model. And if you don't have the model, actually there are ways that and if you don't have the model because someone just provides a public API to the model, Sas, I don't know if this was part of the lecture, but there are ways to try to replicate. These are like the black box, attacks compared to the white box. White box means I have the model, black box means I have an API, but there are ways of trying to replicate the model by having unlimited access to it. You did, okay, you're not. Okay. So I know I might be going very fast, we're not touching main details. It's about going through different, issues around responsible AI and giving indicative examples of what happens. Okay, and always, when there is a potential attack, typically in the literature, there are defense mechanisms. Okay, there are indications that overfitting is typically responsible for such a leakage. So ways to avoid overfitting might, prevent someone from managing to do this inversion, like drop out, early stopping, or masking random parts of the training examples. Yeah. Other techniques are borrowed from another field of differentiable privacy. That okay, maybe we're not going to talk about that, but there is about like adding noise to your gradients during training. Okay, and even though that's a kind of different privacy task, there are signs that somehow it can handle model inversion, but to a very, very weak extent. Or other common example is trying to polarize and reduce the amount of mutual information shared between inputs and internal representations, right? Because this is this is something that would normally encourage leakage, or maybe the private part of the inputs, the sensitive part, and your internal representations. Any questions so far? But the idea from this formulation here is that, okay, this formulation is very similar to what you were studying in the lecture of the adversarial attacks. It's just it's a different objective, and a different task. So other kinds of attacks just mentioned is the model stealing attack that I mentioned. You give a public API, and someone tries to replicate the functionality of your model by having unlimited access to it. Or membership inference attack, that you're trying to predict whether a particular data point was part of the training process. And indeed, there's some ways to achieve that to some extent, and some applications where this can be sensitive information. Okay, we're not going to cover really this in this context, but we're coming back to it in the context of intellectual property. Someone owns data, yeah, training data, models, and maybe even generated data, right? Maybe some of you were exposed to it, yeah. I don't know. I see people smiling, laughing, yeah, because it became maybe a bit viral. There was public discussion. Right? There was a trend trying to use online generative models to produce images in the style of Studio Ghibli. Yeah, I'm not the best to talk about this, but we have very good candidates in the audience, probably. Yeah, and of course, the more philosophical or legal topic is: can a style be copyrighted? Yeah, does Studio Ghibli own this style? How do you define a style? Or there is another question, the model was trained on Studio Ghibli images. Did they have the right? Are these public domain images? Did they have the right to train? So for sure it opens, whole legal, ethical, philosophical topic, but later on we can talk a bit about some technical aspects of it. Yeah? Or other aspects. You have those data sets that are trained on a huge data set of 5 billion images, yeah, of text and image pairs. Yeah, this is crawled from the web. That's a huge common training set. Okay, and then I went to Wikimedia Commons, which is one of the richest source of public domain images, and it has only 120 million. And not all of them have, useful, their images. They don't have the useful captions next to them. So one is to wonder, how many of these images, does someone have the right to crawl them and train a model that is supposed to be, their ownership afterwards. Or other, because, DeepSeek came out, hopefully you have seen, from a Chinese company, another, like a large successful LLM that you can chat with, and there were speculations, or I don't know, US trying to throw trash on Chinese companies that, they trained on the output of ChatGPT. They produced a lot of data for free with ChatGPT, and then this was trained data for their model. Can you prove that? So just indicative examples, right? Watermarking images. Maybe in some domains, you might want to be able to prove that someone performed training on your data. Okay, there's the general case that you might want to do this for any image, but if you have, like copyrighted data, you might be able to do something more. Okay. So, and how to include a watermark in the image, and that's like a very active field. How to include not visible, the common, the widely known watermarks, but invisible watermarks. Like now we go back to the techniques for adversarial attacks. It shouldn't be visible in the human eye, but it should encode some fingerprint, the ID of the owner. Okay. That's a quite interesting field. And then what is the goal? That then, you have like a fingerprint recognition model that is able to recover that and say, this is fingerprinted. You took my photo, you cropped it. And now I can still tell that you did that. But now we're going back to the case of trying to predict whether someone trained on your images. So this interesting ICML paper, what it does is that, in one case it assumes that you have access to the feature extractor, and anyone would use the same. And then you optimize what you add in the image, your watermark, your invisible, so that the representation will shift by this amount. It will become phi of x plus a times u. Okay, you have a vector u and a magnitude a. By the way, I'm showing the watermark here, which is kind of visible because it is multiplied by a big factor so that it's visible in the human eye. Otherwise, it looks pretty close to that image. And then the white box attack, that you assume that, the person that stole your image has the same representation, simply relies on some statistical, hypothesis test there, and they test the cosine similarity between the classifier vector and this vector u. Because if this is part of your training image, then this tends to align, it will align your classifier vector with this vector u. Or there is black box setting where you don't have access to that, and the only thing actually you can do, which is quite interesting, is that okay, if you have access to the loss, you pass the original image, you pass the watermarked image, and then you compare the loss. So the watermark, the representation of the watermark is really distorted in a way that affects the feature space, so that you expect to observe a difference. So this is like, the watermark is an attack that you expect to generalize to other architectures. Then watermarking models. Okay. I have a model, I release it with a license that anyone that fine-tunes it should give credit. Okay. So, but sometimes maybe there is a lawsuit, and you need to be able to verify whether someone fine-tuned your model. So there has been watermarking approaches for networks, where actually more effectively you do it during the training process, where you have your standard objective function plus some other that what it focuses on is injecting again some fingerprint, but now in the space of weights. In a simple case, you can see this, that you take the weight vector, you pass it through an MLP that should be predicting that, yeah, okay, I find the fingerprint here. So that you can do that for another network in the future. You pass the weight vector and say, do I detect the fingerprint or not? It's a binary classifier. And they saw that, okay, interestingly, this doesn't compromise performance on the main task, and is also robust to fine-tuning to some extent, because fine-tuning means I don't, train the model as much as when you train from scratch, but you stay nearby the initialization given by this model. Or another interesting case is trying to protect you when you have a public API to the model, and then someone can query and get access, but the model still in attack was mentioned, that given unlimited access to such queries, someone might try to replicate. Yeah? An adversary will try to replicate the functionality of the model and use inputs and outputs as pseudo labels. So again, the idea here is that, like, somehow, unfortunately, you have to compromise the performance of your model, yeah, by perturbing the outputs, yeah, giving fake output from time to time, and there is a balance there of how often you do that, so that you don't compromise, in a way that you can identify that the train network actually it's a result of your own outputs. At high level, there is a hash function that decides for which examples to do that, and another hash function that decides, what is the perturbation, kind of something like reshuffling some of the top probabilities. And then there is an interesting verification process that you take a model and you test it over a selected set of examples that qualify for the first hash function, and you need to see whether it was actually deceived. And this all relies on the ability of deep networks to overfit to an amount of incorrect labels. There have been papers and studies about that show how, interestingly, the model will memorize such incorrect labels to some extent. Okay, maybe anyways we're going high level, we're skipping that. You can also watermark generated images, right? Yeah. So that you know whether an image, a fake image was generated by a particular object. And now, just as a closing without closing slide without any technicalities is that, okay, here, okay, the authors of this work mapped the energy into joules, energy consumed over time, and mainly to show that, of course, improvements, solving, the tasks in a better way has been achieved, of course, with more training data, with better architectures, but at the end of the day, by consuming more and more energy. Yeah, the scale of the x-axis is logarithmic here. And also they have an interesting comparison here. Okay, they say, look, okay, this is like almost a flat. Okay, it decreases very slow if we fit, the performance of all models, but if we fit the best performing models, it's something that grows quite fast. And this peculiar comparison is the energy that needs a human, to survive the day. But this is the energy that a human consumes, with interactions with all kinds of machinery. But what you see is that actually this grows pretty fast, and this ends in 2021. So if you extrapolate, you will already see that it has surpassed, and it's it's heading there. So the message here is that that's really quite not sustainable way of working on AI, and it has a big cost on on internal consumption is like, let's say, the food that you consume. That's why they mapped everything in yeah. That's why I call it peculiar. Okay, it's like consuming electricity. Yeah, interacting with all. What is your energy footprint during the day or every second? Actually, average. Yes. Yeah. Yes, and this is over time, kind of. Okay, how much energy does a deep like burning? Ooh, I think only electricity, but my answer might not be so accurate. Okay, I'm missing the reference here. It will be added. The reference from which work. So this shows that really this happens in a non-sustainable way, and the standard performance metric is accuracy, while there should be a clear trade-off that is studied there. And sometimes someone needs to oblige you to work on a different regime, and this was what happened with DeepSeek. That as a Chinese company had it didn't have access to as many GPUs as American companies. Nevertheless, they manage their own way to produce as good results with much less compute. So, any other questions? We can finish it with maybe a bit romantic motto that AI belongs to the world, not the other way around. So it has to be sustainable, and that's not what is happening right now. I mean, sustainable in many ways, for the planet, for the society. Well, there's correlation and causation there. Yeah, okay. Yeah, but yeah. Okay. That's the end of the lecture, of course, the whole course. So Sasa, I don't know any information to the students. Yeah. Well.